Uh-huh.
Okay, I started the recording. Yeah, so let's dive into. So, self-supervised learning from images with a joint embedding predictive architecture. Joint embedding. So the fact that it's joint probably means that we may have, I don't know, two modalities that we're using. I don't know. I don't know. Abstract.
We'll see.
Can you see right? Can you see the paper?
Yeah, yeah, yeah. Yeah, yeah, yeah.
Super. So this paper demonstrates an approach for learning highly semantic image representation without relying on handcrafted data augmentation. We introduced the image-based joint embedding predictive architecture, IJPA, a non-generative approach for self-supervising learning from images. The idea behind IJPA is simple. From a single context block, predict the representation of various target blocks in the same image. A core design choice to guide IJPA towards producing semantic representation is the masking strategy. Specifically, it is crucial to sample target block with sufficiently large scale semantic and B, use a sufficiently informative spatial distributed context block. Empirically, when combined with visual transformer, we find IJPA to be highly scalable. For instance, we train VAT Huge 14 on ImageNet using 16 A100 GPUs in under 72 hours to achieve strong downstream performance across a wide range of tasks, from linear classification to object counting and depth prediction. So I'm curious to know on which data set, right? Because so VAT Huge is huge for
It's
visual
huge.
models, right? Yeah, it makes sense, right? But I don't remember the number of parameters though. It's like 150 millions, right, or something like that. That
Let's
range.
check it online. I don't remember.
Yeah. Yeah, I don't remember
But
either.
in
So
any case, I think this approach is very, very smart. I mean, compared to the other ones. Um, I mean, I read all the paper. I mean, it took me like 4 hours because I needed to understand every single piece of the paper. And yeah, I mean, it's quite interesting, their approach. And I really like the fact that they don't use data augmentations. I mean, custom data augmentations. So that's why they, let's say sped up the everything, you know.
yeah, but
Um,
in May, how do you pronounce it? I don't remember. Do they use data augmentation though? I don't think so, right? Or do they?
where? Oh,
In
this one. Oh,
Yeah,
MAE. No, because they use another approach,
yeah, that was
which is,
the masking.
yeah, it's like a generative approach, you know.
Yeah.
It's like you build, I mean, you try to, let's say, generate the patches that you mask during the training.
Yeah.
And so it's different, the approach, because I mean, in the next sections what you can see is that IJPA is an approach, belongs to a family of some approaches, while the other one, MAE, belongs to the generative approach. So
Um, and what about
the
iBoat? I haven't tried that
eyeball,
one. I don't know if you can
let
give
me
like
see.
summary if you already did that before.
No,
Otherwise,
but
it's fine.
what I'm seeing here is that they use some kind of BERT pre-training.
Okay.
So
Okay.
yeah, maybe it's like it's not a generative approach, but
Some sort of
let
like
me see.
uncontrasted learning, right? So similar
Yeah,
to clip,
I
let's
mean,
say.
yes, not, yeah, yeah, something like that. Maybe not contrastive, but pure self-supervised,
Okay.
like Dino or this one. So what I see here in this paper is that they mix a little bit of, keywords sometimes, and let's say topics. And also what is interesting is that LeCun released like the self-supervised cookbook, in which they try to give to the audience, to everyone, some kind of common words and common topics, and how to say and how to talk about things in self-supervised learning. But here they kind of mix together the things. So again, I needed time to
Okay.
understand everything. But
Yeah, I mean it's
So
a big
you meant to
topic,
say
right?
that this paper,
sorry, can you repeat, please?
you meant to say that this paper is not written well curately,
No, it's
properly.
it's well written, but in my opinion, there are some concepts and words and topics or way of saying things that um, are not consistent to the self-supervised cookbook that LeCun wrote like
Okay,
a few months ago. So
okay.
that's my opinion, but I'm no one compared to LeCun. So
We are
No,
just,
no, I
yeah,
get it.
we are just random Jedi's here. Okay,
yeah, just random
so
people.
so
Yeah,
let's
talking
have a
about
look
computer
at
vision.
the introduction, and if we think that is not worth it, I guess that we can skip it. So, in computer vision, there are two common families of approaches for self-supervised learning from images: invariant-based methods and generative methods. So I think that the generative methods are the most used one, and the invariant space methods, what are they? Damn, I don't remember. Maybe let's
So
see.
I can give you some references. So the invariance based methods are like Dino,
Yeah, and
uh,
BYOL.
You know.
So
Dino,
this one I know.
or
Yeah.
CLR, or I don't know, like
Okay.
Bootstrap your own latent.
Sim
So
CLR.
yeah, so
Yeah.
So Sim
CLR,
CLR is a different paper, na?
yeah, it's a different paper, but I guess I think it belongs to the invariance-based methods.
Yeah,
Okay.
yeah. So like with Dino BYOL, you basically take an image, you create two views using data
Yeah,
augmentation, and you
yeah,
have two CMEs networks. Like one is the one that you train, and one is I think it was called a lag representation of the other. So basically, it just contain an exponential moving average of the weights of the model after training, and you're basically trying to match the
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 embeddings.
representation,
Yeah.
yeah, the bendings.
Mm-hmm.
Yeah, I remember. I actually used BYOL before. I remember that I read that one, and I guess when it was released, it was kind of it was kind of cool that it worked, because I think with Sims CLR you need to have also the negative sampling, right,
Yeah, yeah, you have
to
to. Yeah, yeah, yeah.
preventing collapsing, if I'm using the word correctly. There. Yeah. Okay.
It's
So
not
yeah, and
collapsing using
it's actually here.
BYOL. Yeah,
It's actually
yeah,
here.
yeah. Right. Yeah.
Yeah, so invariance-based pretending methods optimize an encoder to produce similar embeddings for two or more views of the same image. With image views typically construct using a set of handcrafted data augmentation, scaling, cropping, and jittering, and others. These pretending methods can produce representation of a high semantic level, but they also introduce strong biases that may be decremental for centering downstream tasks or even from pertaining tasks with different data distribution. Okay, interesting. I would like to know like which strong biases, because I'm
Yeah,
curious.
there is the reference, the number two. I guess he's referred to the paper. Yeah. Didn't
Didn't
even
even.
classical.
Okay,
Oh yeah, maybe I read something. Let me see.
this is pretty new as well. This is pretty new. It's 2033.
Oh yeah. So yeah, I took some notes while reading the paper. So, uh, but I mean, I'm gonna summarize what this
Mm-hmm.
paper is talks about. But basically, what this paper says is that if you have an imbalanced data set, what you can produce, let's say, is that you have some kind of strange, let's say, distribution at the end of your pretext training. And
Okay.
so maybe that's why that's what happened in that reference, in that paper, what they
Okay.
are trying to, let's say, show.
Makes sense.
But it's a very let's say, lightweight summarization of what that paper is about.
Okay. Give me a second, because I need to turn on the fan because it's too hot here.
Yeah, 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 I know.
Why we stop at this one? Let's move forward.
Okay. Okay. So often it is unclear how to generalize these biases for tasks requiring different level of abstraction. For example, image classification and distance segmentation do not require the same biases. Additionally, it's not straightforward to generalize this image-specific augmentation to other modalities such as audio. Yeah, of course. Um, Cognitive learning theories have suggested that a driving mechanism behind representation learning in biology system is the adaptation of an internal model to predict sensory input responses. This idea is at the core of self-supervised generative method, which remove or corrupt portion of the input and learn to predict the corrupted content. Okay, we know that. In particular, mask denoising approaches learn representation by reconstructing randomly masked patches from an input, either at the pixel or at the token level. Mask pre-training tasks require less prior knowledge than viewing variance approaches and easily generalize beyond the image modality. Yeah, because like with text, you can do the same thing. You just mask part of the words, right? And I think with audio, I'm not an expert there, but you can do the same thing. And I think Data Chubek was actually doing that, right, if I'm not mistaken.
And also iBot is quite the same, but also masked autoencoder is quite the same because it does
It's the same
basically
thing,
the same
basically.
approach. Yeah, it's the same thing. That's why they call it generative, right?
Yeah, yeah. And it's pretty cool because it makes way easier, you know, to work with different kind of data with the same architecture. Okay. However, the resulting representation are typically of a lower semantic level and underperforming variance space pre-training in of the shaft evaluation. And Mr. Robot, I don't remember if you were there the last time, but we had a presentation from Sam who made a paper showing how to increase the semantic. Yeah. So that was very interesting. And Ricardo, if you want, I can share that paper with you. So basically, what it did was taking, the MAE and train it in a way that is actually able to have better semantics. Because if you look at the patch that MAE is going to fill, they look very blurry, right? But then I don't remember the approach. I have to review the paper, but basically, when he ran his approach, he was able to get very good pixel level images within the patch that he has to predict. So basically, increasing the semantic, and this also showed that you get a very good boost in downstream tasks.
Okay.
It was very
Okay.
interesting.
Yeah. Check the paper, please. Yeah.
Yeah, he meant by like the activation function quietly aligning with the semantics of dog or cat or any object. Means usually what happens that you take a activation function C, then you see that it's quite out of context. The nose is not there included in the activation function, but in his paper it was there. So
yeah, it was.
a good
Yeah,
paper.
I think that it was showing the attention on the image. Or that was the version function. I don't remember, but like the blue image with the yellow stuff, right? Yeah, I think it was that one. Well, okay. So let's continue. It's lower semantic and underperforming variance-based retraining of the shelf evaluation, agility linear probing, and in transfer settings with limited supervision for semantic classification tasks. Consequently, a more involved attention mechanism, hand-to-hand fine-tuning, is required to reap the full advantage of these methods. In this work, we explore how to improve the semantic level of self-supervised representation without using extra prior knowledge encoded through image transformation. Okay, so this is the important part. To that end, we introduce a joint embedding predictive architecture for image IJPA, and an illustration of the method is provided in figure 3. The idea, so here we have figure 2, here it's talking about figure 3, so maybe we have to have a look. Yeah, okay. So here it's talking about the methods, right? So common architecture for self-supervised learning. The system learns to capture the relationship between its input. The objective is to assign a high energy, large scale scalar value to incompatible input, and to assign low energy, low scalar values to compatible input. Yeah. A is joint embedding architecture learn to output similar embeddings for compatible inputs x and y. So here we have like two views of the same image. We have two encoder.
This is like that. This is like Dino is the common approach with me. Yeah.
Yeah, and then the generative architecture learn to directly reconstruct a signal y from a compatible signal x. Using a decoder network at this condition of possible data variable z and facilitate the reconstruction. Okay, makes sense. And then we have the joint embedding predictive architecture. Learn to predict the embeddings of a signal y from a compatible signal x using a predictor network that is conditioned on additional possible little variable x to facilitate prediction. Okay, so here we have an encoder only for y and a predictor, and they are basically predicting two embeddings, and then we have a loss. And this is probably this is joint embedding, right? Because we have two of them, right? And predictive because I guess we have our predictor, right? So yes, it makes sense.
Yeah.
At least for the image.
So y is text or x is text?
I'm sorry?
Which is linguistic? There must be two, no? Joint embedding. One is image and one must be text.
No, I think they are both images.
Yeah, they're both images. Yeah. X and Y are the same image, but X it's like part of the image, and Y is another part of the image. You can.
So this is similar to something that was called patch-GAN. I guess that was a GAN that was trained on patch of images, and it was able to basically predict a patch of images. So I guess, I don't know if it can be something similar. I remember that. I think it was pretty cool at the time.
To me, it looks like a masked autoencoder, but not in the pixel space, but in the latent space.
Okay.
Let's say it's like an adaptation of the masked autoencoder, but in the latent space. Because you see they add also the latent variable z, as they do in the generative architecture. I mean, this is going to be the positional encoding of the patches, basically, just to give you like a spoiler. And so, to me, it looks like a mix. But the smart thing is that since you're not going into the pixel space, you reduce the compute power needed to, and also the training time, of course. That's the smart move that they do. And since you don't use data augmentations, also, I mean, the method is incredibly fast compared to the other ones.
I guess that you are just removing a hyper parameter that you don't want to test, right? So it's also, I guess, fast to find the right amount of hyperparameters because you have one less. I say. Okay, so the idea behind IJPA is to predict missing information in an abstract representation space. Okay, this is what you were saying.
That's the point.
Given a single context block, predict the representation of various target blocks in the same image. Okay, where target representation are computed by a layered target encode network. Okay, compared to generative methods that predict in pixel token space, IJPA makes use of an abstraction prediction target for which unnecessary pixel level details are potentially eliminated. Okay, so just in the embedding space, thereby leading the model to learn more semantic features. Okay, another core design choice to guide IJPA towards producing semantic representation is the proposed multi-block masking strategy. Yeah, I'm kind of confused here. So why do we need a predictor? But maybe we will know later. But like, so why do we need a predictor here? And why we cannot just from the encoder get the S? Oh yeah,
Yeah,
yeah. It's a stupid question because you are trying to predict the embeddings
yeah,
of
right.
Y from X.
Yeah,
Oh
right.
yeah, okay, makes sense. I-
I
Interesting,
mean,
interesting.
it will make more sense when we see the, let's say, the real architecture. I mean, when
Okay.
we see the image and they explain the methods. But at the beginning, I was also confused. But then he was like, "Oh my God, this is so smart."
Yeah, it makes sense. Yeah, DP fine.
Yeah.
Okay, so multi-block masking strategy. Specifically, we demonstrate the importance of predicting sufficiently large target blocks in the image using an informative, spatially distributed context block. So by context block, they just mean a part of the image, I guess. Um,
Yes, yes, yeah.
throw
So,
a,
so you take a context block, which is, let's say, a patch of the image, and then you have target blocks. And what we have to do is predicting the embeddings of the target blocks based on the context block. So this is like the old paper,
okay,
basically.
okay.
Yeah.
Yeah, so I guess that here we can skip a little bit because here is
Yeah, yeah,
just,
yeah,
we are
yeah.
good
What is
and
this
we're cool.
off-shelf
That's just
representation?
Sorry?
Off-shelf, they use this word off-shelf representation. Like, what could be the meaning of this thing? Off the shelf, yeah, like
That they are
where
just,
ME where 36.
I guess that they are just giving to you, you don't need to learn them again, or like, I don't know. So what would be the
To me,
right?
yeah, to me, it's like the keyword is handcrafted view augmentation. So you don't need to, let's say, have specific augmentations for your problem, but
Ah,
you just need, let's say, your image and that's it.
okay.
Yeah, but they
This
are
is what
just
I
running
understood.
experiment on ImageNet 1K because this is what I was talking about with Sam, the guy that made the paper I was talking about. Is that all these kind of self-supervised methods, they always use ImageNet, right? And I asked him like, why is that the case? Because in ImageNet it's very easy to mask off because you have one image and there is one subject and it's in the center and it's big. So statistically, if you mask a part of it, you will still have a lot of context to be able to understand how to fill that part. But if you have an image with 10 dogs, you may just going to mask a dog and you'll lose the object there. And then he told me that it's true, but they usually, I mean, even just with ImageNet, you are able to learn a lot about images. That's
Concepts.
why it's used.
Yeah.
But that is always kind of weird. Like in all the papers, I always see most of the paper that are doing these self-supervised things. Not probably all of them. I always see pre-trained on ImageNet, and that's it, right? Uh,
Mm-mm.
that is kind of confusing to me because why? So what would happen if you run the same approach on a subset of Coco, for instance, which is shitty, but you have a lot of subjects or objects around, and you may mask a full, like assuming that I mask a dog, and then I want to generate what was inside that patch. How can I know that there was a dog there? Like there is no context for me. So then the loss function will just penalize me, even if it was not fair, because I cannot know that there was a dog there because I masked the full dog. So I was kind of wondering about that.
But maybe what happens is that everybody is using ImageNet. So I mean, just to give references to people, and let's say have a good paper. Maybe what they do is that, okay, everybody uses ImageNet, so okay, we're gonna do the experiments with ImageNet. So that's why. But I agree with you,
Yeah, like
and I totally agree with you.
I agree that that must be the reason. But I kind of wonder, like, why nobody is saying something in their paper, like say, okay, we kind of noticed that in ImageNet we only have one subject, basically almost always one subject per image, you know, and yeah, so just say something in these lines, you know, because that could also mean that your approach works only if you pre-train on something that, you know, similar to ImageNet, in a sense that you have one subject big in the image and in the center. I don't know. I don't know. Do we need to read the background though? What do you think?
I don't think so. Maybe we can go very, very fast because I mean it's
Yeah,
talking
the
about
joint
self-supervised
embedding
learning approaches.
architecture.
Yeah,
Yeah, so this is the Dino, BYOL, etc.
yeah, Dino, yeah,
Generative
yeah. The narrative
architecture.
architecture. And then
Yeah,
yeah, and then they talk about their approaches. So, yeah, we can skip this part, I guess.
yeah. Okay. So here we have figure 3 that was talking about
Yeah,
before.
this is the architecture basically.
Okay, so let's see. We have the context. Yeah. Uh, as I was saying, subject big in the center of the image.
Yeah,
So we encode it, and let's
then
see. We
then you
also
have
go
the target blocks. Under I mean beneath you
because
have the
they
target
overlap,
block.
right?
Yeah.
So here you are going to add that
Okay,
part.
I can explain you.
Yeah,
So
please.
what they do, yeah, what they do is that they, of course, as I mean, VIT is pretty clear, but let's say flatten the patches. I don't know how to say in English,
Yeah,
but
yeah, yeah. It's, I
and
guess.
and each patch has a position, right?
Mm-hmm.
And so what they do is that they produce the context block, and they pass the context blocks to the context encoder, and you get the context embeddings. For the target encoder, what they do, they produce these targets. No, sorry. They run the target encoder to every patch in the image, okay? And then this is clear after you read, I mean, when you read the paper, but so they uh, pass they give all the patches to the target encoder, and then they, let's say, randomly select with some kind of let's say logic behind some patches, okay, some embeddings of the patches, okay, maybe some consecutive ones. And what they do is that they give to the embedding of the context encoder above, they give the information of the position of the patch that they need to, let's say, predict. So the predictor will have as an input the embedding from the context encoder, which is the grade one. Yeah, right.
Mm-hmm.
And then they have these, let's say, the position encoding, which is the Z in the diagram in
Okay, and
figure
then it
one.
has to
And so
predict
what
the
they have
right
to do
side.
is basically predict the embedding. Yeah, right. They predict the embedding relative to that position. So basically, is the yellow one is going to be the embedding produced by the target encoder for that position, and
And
so
that's our
and they do basically like
yeah. And that we're going to predict this one, and then we're going to run the loss with these two guys, right?
no, they're going to run the loss between the yellow one on the right side of the predictor, and yeah, the, let's say, the one on the target encoder, the bounding box yellow, the yellow bounding box, yeah. So you see, and they are gonna run the loss. It's L2 loss, or
Ah,
L2 in
yeah,
English.
yeah, yeah. Okay, so this is okay. So this is the predictor. It predicts this, and then we run the loss with the same
Yeah,
the true one. Okay, okay.
yeah, but
Why I can't hear you anymore? Wait a sec. Oh boy. Uh, Sorry, my earphone got disconnected for some reason. I'm sorry, I just have a little issue with my mic. Piece of crap. I think that you're hearing me now because of the webcam, but my mic is not connected for some reason. Damn. Just give me 1 sec. Yeah, it seems that I cannot get my mic connected. Wait, I'm gonna to USB. Where it is? Come on. No, I cannot get it to work. I'm gonna restart my computer very quickly. Yeah, here we go. Okay, cool. Perfect. So yeah, yeah, I think we got the idea here, right?
Yeah.
Okay. So let's jump into the method. We now this yeah.
You're not sharing your screen yet.
Oh boy. Sorry. That's right. Here we go.
Yeah.
Okay. The method. We now describe the proposed image-based joint embedding predictive architecture again. IJEPA illustrated in figure 3. The overall objective is as follows. Given a context block, predict the representation of various target blocks, so the colors here, in the same image. Use a vision transformer VAT architecture for the context coder, target encoder, and predictor as well. A VAT is composed of a stack of transformer layers, each consisting blah 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 blah, self-attention, follow. Okay, we know that. Our encoder predictor architecture is reminiscent of a generative mask autoencoder MAE method. However, one key difference is that IJEPA method is not generative and the predictions are made in representation space. Okay. Somebody drop off. Okay. Targets. We first describe how we produce the targets in the IJEPA framework. Can you see my screen right? Because I'm hearing some weird Discord sound. Okay. In IJEPA, the targets correspond to the representation of image blocks. Given an input image y, we convert it into a sequence of n non-overlapping patches and feed this through the target encoder. Okay, but these patches are overlap. No, okay, yeah, you mean like the overlapping. Yeah, this is the normal VAT stuff. F theta bar to obtain a corresponding patch level representation as y, sy, sorry, and then here we have all the patches, right? Where syk is the representation associated with the kth path. Yeah, this is the normal VAT stuff. To obtain the targets for our loss, we randomly sample m possibly overlapping blocks from the target representation as y. Okay, so from the patches, we just sample some of them, and these are the targets block. We denoted by bi the mask corresponding of the it block. Okay, by the mask corresponding to the it block, and by syi. Okay, wait a second. The mask corresponding of the et block. So where is the et block? The mask. Which mask? I'm getting confused here. They're not
Wait.
masking.
So they're getting M blocks, which are, let's say, basically embeddings of the patch.
Yeah. So let's say this, but in embedded space. So
Whatever.
like
This is just a drawing. To me, it's not like the right one to understand the method, the right method. So what they do is that basically they sample M blocks, which to me, wait, I got confused too. Come on.
It's a
Maybe,
little bit confusing.
yeah, with blocks, they mean, let's say, some patches, some embeddings of the patches that you get together.
Yeah,
Okay,
yeah,
so
yeah, yeah. So
a
like
block, a block is one or more patch. Yeah,
yeah, like the bed of the yellow thing, you
yeah,
know. So this
yeah,
is a
yeah,
full
right.
block of two patches there. Okay.
Yeah,
And BE the mask corresponding of the ET block. Yeah, because I guess we need to mask all the stuff
yeah,
that is not
the
there,
other
right?
part, of course. Yeah, yeah.
Yeah. Uh, and by
Yes,
SYI
that's right. Yeah.
is
It's like
okay,
it's the
okay.
embedding related to the block, masking all the patches that do not belong to the block. I mean,
Yeah,
it's
it's
quite complex.
yeah, it's
It's
yeah,
an
it
overkill.
yeah, it's basically the stuff that you really care about, right? So I mean,
Yeah,
like here, it's also for the audience. So here, this is what we want, and we need to mask all the others.
yeah,
So this one will be the tokens. So let's call them tokens because I guess it's the right time. The tokens that are not masked by this B,
yeah.
that is B, and B I is the mask for the I block. Yeah. Okay.
Yes.
Okay. Okay. So I don't want to get confused by the image now. So patch level represent. It's patch level representation. Typically we set m equal to 4 and sample the blocks with a random aspect ratio in the range of okay, a random scale in the range of 0, 15, 0 to 2. I would like to know how they arrive to these numbers, but they probably have some table showing that. Note that the target blocks are obtained by masking the output of the target decoder, not the input. Okay, so this is very important.
Yeah. This is
Bec
where the fast comes in.
yeah,
Where
and
the fast part
also
comes
because it means so if I'm doing the masking here, right here
in.
in
Yeah.
this embedded space, it means that all like the patch, sorry, the tokens in this block were able to see all the other stuff, right? Because we haven't masked here.
Yeah, you're right.
Yeah, so I guess that's it's a little bit it's different compared to MIE where you mask before, so you're not able to attend to the part that were masked.
You sure you masked before? I don't remember.
In MIE, yeah, you mask before.
Let me see.
In which
Oh, yeah.
paper? UMass.
MIE,
Mask
mask
encoder.
autoencoder.
Let me see. Because I don't remember.
Because it's actually, if that is true, it's actually a very big difference because it means that my block was able, was computed by
Yeah, you're right. You're
attending to
right.
all the other patches, right? So it's carrying some sort of information. No, like yeah,
Yes.
it's yeah, it use other part of the image to compute its own embedding, right?
This paper is by gaming initialization guy.
Is he famous?
The MAE one, the mask autoencoder one.
Okay. Were you able to find out if in MIE they masked before?
Yeah, yeah, you were right.
Yeah, they
Okay.
masked before. They
Okay.
masked before. You don't need to verify.
Okay, cool. Yeah, so I guess this is a nice thing, and yeah, but they're not talking about that yet, I guess. Recall, the goal behind IJEPA is to predict the target block representation from a single context block. To obtain the context of IJEPA, we first sample a single block X from the image with a random scale in the range of 0.851 and unit aspect ratio. We denote by Bx the mask associated with the content blocks X, okay, similar to BI. Since the target blocks are sampled independently from the context block, Mr. Robot, you're making a lot of noise, man. How are you doing
Sorry.
your dishes?
No, I was making something to eat.
Oh, okay. Yeah, since the target blocks are sampled independently from the context block, they may be significant overlap. Okay, so this is the context, right? Oh,
Yes.
yeah, and here, no, okay, so I guess, yeah, so the context is, it's all of this image, right? It should be,
Yes.
so, yeah, so I mean, it will be probably, like 100%, there will be some overlap, right?
Let's see the examples. So yeah, let me see. No, maybe there is no overlap.
Yeah, but this is not 80% of the image, because they say that the context block is between 80 and 100.
Yeah, you're right. 85.
I mean, this, by looking at me, this is like 50% of the image.
Yeah,
Maybe
yeah.
60. So let's say 60. So yeah, so if there is some overlap, it means that both of the encoders, are able to do the attention at least based on some common tokens, right?
Mm-hmm.
Yeah, and then I don't know if these two models are actually the same or some trick there.
They are the same, but the target encoder is updated with the exponential moving
Yeah,
average.
yeah, okay, makes sense. I was thinking that actually was the case. So then it means that they are actually creating the, yeah, so this is kind of interesting if you think about, because compared to the previous approaches, now with the compared with the two views of the image, you're still having the same image, right? But with the transformer, it's kind of different in the way it works, because here you basically do not have the same image. So by same image, I mean that basically, it's not like you, yeah, I mean it's not true, because in BYOL and Dino they also crop, but here basically you have the same positions, right? Because you're just going to mask the things that you don't want to, like you're not going to resize or whatever, but some position have tokens that are in both of the context and the target. So it means that what is coming out of here and here was computed using at least some common tokens between them. So that is kind of interesting, because it's a different way, it's different compared to CNNs to some degree, let's say.
Yeah, I see your point.
Yeah, I don't know if that makes sense. And I was kind of wondering, so what will happen if you have no overlap at all? So if you don't have an overlap, it means that this guy here and this one here,
Two different images, basically.
yeah, but basically seeing that, so I guess that, to compute this, we mask all of this stuff, right? But wait, we are masking, the patch embedding. So all the things that the models can see is just this part here, right?
Yeah.
And if these two guys, so like with this one and this one, they do not have an overlap, right? So this has an overlap with this one, and this do not have an overlap. So that is kind of interesting, because if you don't have an overlap, you don't compute attention on similar tokens. While if you have an
Exactly.
overlap, you also compute attention using some common tokens. So I was kind of wondering, so what will happen if I just use target blocks with no overlap and target blocks with always an overlap? Will that change something? Like, will the target blocks without an overlap, actually not helping?
We will not
Or
be
yeah.
will not be capturing that deep semantics. Now, like if you see the eye of the cat, so if we don't tell in the model that how the eye structure of the eye looks, then it may be model cannot.
No, I was talking about, so if you have this red box and this image. So each of these token basically it's weighted by how much like how much important is with all the others, right? So that's the attention. So this is it's able, so like this part here is able to attend to this, to this, to this, and this to that, etc. And here the same thing. So like this is able to attend there, there, and here, there, etc. But it's cool because these two parts are common here. So it means that these tokens that are not here are actually seeing some parts that are common to both images.
Guys,
Yeah.
but we forgot to read a line in the paper.
Oh.
Yeah, that's quite important.
Okay, please. Where?
When they talk about context now, go where we were reading. No, in the next page. Yeah. Okay.
Okay, context
So,
here.
okay, we denote by since the target blocks are sampled independently from the context block, there may be significant overlap. To ensure a non-trivial prediction task, we remove any overlapping regions from the context block. That's the key phrase.
But it was cool that without reading this, we were actually thinking about that there could be a problem. So, you know, I guess it was cool that we didn't read that because it forced us to actually think about that and maybe say, yeah, there could be a problem, right? And it actually thought the same thing. Okay, so no overlap there.
No overlap, yeah.
It's trivial because you are using the same information. Some part of it.
That's why in the image above, I mean, the image is these ones. I mean, you don't see any overlap, of course.
Yeah. Okay, sweet. So, okay. Figure 4 shows a sample of various contexts and target blocks in practice. Next, the masked context block. X is fed through the context encoder f theta. It's theta, right? To obtain a corresponding patch level representation as X, and we have the patch level representation. Prediction. So this is, I guess, the missing part that I was not really understanding too much. Given the output of the context encoder X SX, we wish to predict the M target block representation. SY1. Okay, so all okay, so these are all the target blocks, right?
Yeah, they pick 4 blocks.
Yeah.
M is set to 4.
Okay. To that end, for a given target block XYI corresponding to a target mask BI, the predictor G phi, right? Weird emoji face. Take as input the output of the context encoder. So this boy here. And mask token for each patch we wish to predict. The mask and a mask token. What's the mask token?
They're going to explain what the mask token is afterwards.
Nice. Okay, this is a mask token and outputs a patch level prediction. I mean they have to have the same size, so it's output something that I guess has the same number of unmasked patch. The mask tokens are parameterized by a shared learnable vector with hidden position embedding. Okay, so basically you are incorporating this thing called the mask token. You also need to add the position embedding, of course, because it's a token. Since we wish to make prediction for M target blocks, we apply our predictor M times, each time conditioning on the mask token corresponding to the target block location wish to predict. I'm not really sure that I'm understanding what the mask token is doing here.
To me, it's gonna be the position it's like the positional embedding of the, I mean, of course, of the token. I mean,
but you have already all the positional embeddings, that were incorporated here. As soon as you do the embedding, you also add the positional embedding. So this mask token is something that you add.
It's another one. We can see the implementation afterwards.
Yeah.
I didn't
Yeah.
see the implementation, but maybe, yeah, the code maybe tell us everything.
I mean, to me, so when you have a new token with a name in English, so it's usually something that adds some information, like
Mhm.
help. So I guess you need a mask token to understand which mask you want to predict, right? To some degree, because
Yeah.
how can a predictor know which mask I want to have? Because here the input is the SX, oh, sorry, the input, the predictor, yeah. So the input is SX and the mask
Oh,
token.
yeah,
So
but yeah, these ones are like it's basically the mask of
what
one of your
you,
blocks.
okay.
Maybe, might be.
Yeah,
I
so
mean,
because
yeah,
here I can see BI, so it means that
yeah,
you need, yeah, but this is kind of confusing. Like, what's the, I don't know. I mean, I guess it's, I mean, you need to have some information on which mask you want to predict, right? And the mask token is telling you that information. Now, how they did it, it's still little mystery for me. But yeah, so then we have the loss. Okay, normal altitude distance. The average altitude distance between, okay, so this is straightforward, right? The parameter of the predictor phi and the context of the theta are learned through gradient-based optimization, of course, while the parameter of the target encoder theta hat are updated via an exponential moving average of the context encoder of the context of the parameter. Okay, so this was the old method. So yeah, it's kind of interesting because it's some sort of a mixture between the invariance one and the generative
yeah.
one, some sort, and it actually makes a
The
lot of
Z is
sense.
the key. Yeah, the Z is the key to have like this kind of mixture between the two approaches.
Yeah, and like I mean, from a computational point of view, since here you have a decoder that is usually, I mean, it's not usually too big, right? But here, like, you need to have double the encoder, so probably from a memory point of view, it's lower, but from a gradient point of view, it could actually be the same because you're not computing the gradient for this one, right?
Yeah, right. So to me, you have only, let's say, two big updates, which are the X encoder and the predictor. Maybe the predictor is going to be an MLP, I guess.
Yeah. No, they say that it's a transformer as well, and it has to be a transformer
Oh
because you
yeah, yeah,
have
right,
the
right,
mass
right. It's
token,
a
right?
smaller, yeah, yeah, it's a smaller transformer. Yeah, 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 right. You're right. It's a smaller. I mean, the encoder is like the huge VI,
Yeah, the
yeah,
big boy there.
whatever, and yeah, and the predictor is like a smaller version. Like
Okay.
you have an embedding of 384, I guess.
Yeah, 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 yeah. No,
By the
yeah,
way, I
yeah.
checked, and the V is huge.
No, no, it's no, the embedding for
Yeah,
the VAT use is 1768.
yeah, yeah, I know, but the
Sorry.
number of parameters is like 600 million, so like
It's really
632.
huge, man.
Yeah, it's huge. It's huge.
Okay, so let's
Yeah, let's see the
see.
experiment. Yeah.
So this is top one. So this is linear evaluation. So they freeze the encoder, the model,
Yeah, yeah,
and they
totally, yeah.
just, man, they have this.
It's huge.
Yeah, but yeah. So let's so let me take the paper from Sam because I think he had better results than that. Uh, yeah. So let me take it. So let me check his paper very quickly. Because here it's this is the age. It's 2%, right? Uh, so let me
I
quickly.
mean, it looks good.
Yeah, but
Yeah.
see the number of epochs they
Yeah.
trained the model.
Right.
Yeah,
Right. Right.
that's the key point.
That's indeed the Q point. Yeah, yeah, you're 100% right. I mean, even if it was the same uh, value, it still would be way better. And it's kind of crazy that the base one. Oh yeah, I mean they just train for longer, I guess, because they can afford it. Uh, Okay, so it's okay. So some paper that was the other paper that I was talking about, uh, linear probe with VAT base is 78.1.
For what paper?
Another one, so let me share that as well. Uh, so the paper that was talking about before, that
This
was,
is the one.
yeah, so let me also add this to the browser. How can I? Okay. Yeah, so he's a paper from Sam, is a member of the community, and share it. And basically, so this is what we were talking about. So if you look here, this is basically uh, what you will get with MAE using the mean square error, and this is with his method. So you see that it's really able to get the right semantic of stuff that is going on there. And this is the yeah, VAT base. Dino VAT base. They don't show that, but MIE, okay, 67.8. That is the same. Yeah, in the other paper we have 68. I guess I don't know. But if you see here, you get 78.1 to the base, that is higher than the huge on the other paper. Then this is not a fair comparison because I guess here they had to train for longer. So let me see, GPU 8 NVIDIA GPU, how much time? It was actually, yeah, I need to ask him. So let's see if I see hours. No. But this was also very interesting. Now imagine if you can somehow combine. No, I don't, because I think that this is already in the fall that you're actually gonna use the latent speed. Yeah. So this was very interesting. And I kind of wonder, like, this is a huge jump, right? So like you basically go for 67 to 79. It's same model, right? Same model. Like, I mean, it's not completely the same model, but the VAT base is the same.
But they also use more data, right? Because they use also the DALI one.
Yeah. So yeah. So this one. So this one is comparable. Yeah. I don't know. I think it was interesting to also show this as well. But yeah. So let me
Yeah,
really.
what you're saying is that by changing like the loss function, maybe you can
Yeah,
get better.
so what they were doing here, I now them I don't remember because it was a little kind of complicated. But they are basically somehow, man, I don't remember them.
But it's okay. Please link the paper so
Yeah,
that I can look.
yeah. I'm gonna send
I
that to
sent
you.
the paper here.
Oh,
Yeah,
okay.
there is already a post on the paper channel with that one. I just
Oh,
posted it
yeah,
there. Yeah, but it was kind of a bummer, because it's not as famous. Oh no, wait, I'm sharing Discord now. Window, where it is? Okay, it's this one. Okay, sorry. Okay. Okay, so the takeaway is that it takes way less compute, right? But here we have in epochs. We don't have it in hours, right?
Yeah,
I
but
guess.
what they claim is that also, let's say, GPU time is less because the model requires less time, computing time, actually.
Okay, but
I
why
mean,
it
they wrote in the
requires?
paper. No, I don't remember, but they wrote it sometime somewhere in the paper. Maybe
Yeah.
you can see if you go like the beginning when they have like the 3 bullet points with all the outcomes of the paper. Maybe they say something. Yeah, here,
Mm.
if I remember correctly.
less than 1200 GPU hours.
Yeah.
If less GPU, it means it is an efficient algorithm. But that doesn't guarantee that you are capturing very deep semantics. Still, you can miss it.
So I kind of wondering. So I also pinged Sam in the chat, which is the guy that made the other paper, and just say, you know, how much CPU hours did you use? Because I'm kind of curious here. Okay, so let's see some more tables here. Methods without data augmentation. Okay.
The
Data
other one is like
this is
we just
the
14 images per class per label. So
this is still very good.
yeah,
Still very good. And I
iBot is quite interesting. But their claim is that with iBot, what you have to do is having let's say data augmentations, let's say that fit your problem. So their
yeah,
claim is that
but you're
I know, I
just
know.
like in
Their claim is
practice.
that their claim is that okay, we can do let's say quite comparable to iBot, you know, even though we are not using data augmentations. So yeah, that's their claim. If you
This is
see
very
in
huge claim.
the experiments, when they write about the
Well,
experiments,
but
they
like I guess if we have to be 100% honest, their data augmentation is, I guess, how you sample the context block somehow, right? If you think about that, but still, you don't need it to change it based on the domain.
yeah, yeah.
In theory, yes, right? Because if you don't have images with the object in the middle, then you need to
True.
change how you create the blocks because you don't want to completely remove the object, right? It's the thing that we talk about that. Uh, yeah, but since you're working in the semantic space, like here, if you look at this, no, okay. So from this context, I can infer almost everything in a pixel level way, except for this thing, right? Because like this stuff here is not here. So I would like to see some sort of metric or comparison, or like how good is the loss, right, in the cases in which we don't have something that can be visually inferred by the context, right? So what I'm talking about is like so this part here, right? I don't see it here. So this is like a car that is, I don't know, is doing some weird stuff. But this boat here can be partially inferred for this part here.
Well,
And
what they claim in the paper, I mean, they do other bunch of experiments.
so let's
If
have
you
a look.
go like go down,
Okay.
yeah, these ones are the experiments. So what they do, just to give you like a very brief, let's say, context, is that they train like a decoder that has to generate the part of the image that you see in the green bounding boxes based on what you give to the model. And so what they
That's
claim here
great.
is that
Yeah.
what they claim is that okay, with this method, as you can see, we generate part of images, you know, that you are asking about. See the
This
dog,
one.
the
Yeah.
husky one. So what they say is that okay, even though of course it's not like the
Yeah.
perfect
But the
part of
semantic, it's
the
correct.
semantic is correct. Yeah, right.
Ah.
Also with the car, also with the bird. You see the bird, you have
Yeah.
the
Yeah.
back of the bird, which yeah, is different, but the semantic is correct.
This is
So
sweet.
what they-
Yeah.
Yeah,
Also here you don't see the bridge at all, but the semantic is correct. You know, there's
it makes
probably
sense.
some.
It makes sense because you see green areas, and so what you let's say generate based
Mm.
on the embeddings from the model is that you understand that there is some kind of green area, so you generate green areas. So that makes sense. But also see the dog, the face of the dog. I mean, also let's say the cheek.
Yeah, this is some
The
very
cheek and the
smart
eyes.
visualization here.
Yeah. This is this experiment here is very interesting. There is another paper that referring to they talk about this approach here, and also in the I'll just say in English, I don't know. After all the references, I don't know
In
the
the
annexes.
appendix.
In the appendix, right? In the appendix, they talk about this method very briefly, but they talk about this method.
Okay.
And the method is, let me see. Okay, RCDM
No,
visualization.
wait a
It's like,
second, with the best size of 16.
yeah, of course, they have a lot of money, of course.
Fuck. Okay, and the section is, sorry?
E, section E.
Damn, it's this is some very good. This is a very good paper, by the way.
Yeah.
Okay.
I mean, I haven't read the paper yet, but
is
yeah,
this?
it's quite interesting. It should be like a generative model that you add noise, and of course, yeah, it's a diffusion model, of course.
Diffusion model are not good at capturing semantics very well. They miss it. They only capture the outline. Means if you ask them hand, they will give you hand, but the ratio of finger to wrist or palm is not
Yeah, but
good.
have you ever?
So
So
for that,
I play a lot with stable diffusion and tricks. So if you use control net and good negative
that's it.
embeddings,
That's it. The control.
yeah,
So control net itself is a specific model, like for depth,
yeah,
space,
yeah,
for everything. They have provided one file.
yeah. But I mean, it's quite crazy how. I mean, it's a game changer, control net, right? Because you
Means
can
I can tell you
control.
from my work, I was doing the work for animation generation. So when you generate animation, then diffusion model with control net do not work well. You need something else
Yeah,
because the connectivism between prompt. So that's a very difficult thing. Means
and
how you are
I guess like also how to be consistent across frames.
no, for the consistency you need to see for CFG scores. So that will help you. And means but that also doesn't guarantee. They have said that this also doesn't guarantee. If you change the seed, then again this thing don't work well. So
Yeah.
there doesn't exist any good explanation, and the field is exponentially growing.
Yeah, so like, do you have some good pipeline to create good animations with
Yeah,
stable?
that's it. Yeah,
Yeah,
means Mid Journey has one edge.
so he will have to speak at some point because I would like to know more about your pipeline because I also would like to generate some animation and uh,
Sure, yeah, I can tell you. Means like we use stable diffusion automatic triple A
yeah,
one
yeah,
one.
yeah, the the
Mm,
the Holy Grail. Yeah, but so for next time, man, because otherwise we're going
yeah, yeah,
out of
yeah,
topic.
yeah, yeah.
Yeah, so okay. Okay. Oh, cool, cool. So yeah. So this is what you were saying, that they are using the features to train a diffusion model. So they're taking the original image, embedding, and then giving the feature to a diffusion model to generate new images, right?
Yeah, it should be something like this. I mean, I haven't read the paper, the one about the method, but I mean, it should be like this.
Damn. This is some interesting.
They,
Yeah.
yeah, it's like two. They have to like two heads.
Yeah, yeah, but I mean, it makes sense. Like, I mean, here the catch is not to be able to generate the best image, but to see if the semantic is there, right?
Yeah. Just to see if the semantic is right. Yeah,
This
that's right.
is pretty good work. Pretty. I mean, this is very good paper. Is there an implementation, right?
Yeah. Or, yeah, if you go on GitHub, you have all the implementations. I mean,
But is there an official one?
yeah. I mean, you can look at it.
Yeah,
If you go on Google and type
yeah,
iJEPA GitHub Meta, I mean,
yeah. I'm gonna share that.
yeah.
Where the? Okay. So
Yeah, on my spare time,
what?
what I try to do is, let's say, put order in these code bases from, let's say, open source code bases, about these methods here, and trying to build my own self-supervised learning library, just to understand, I mean, how to code this kind of stuff. Because
Yeah,
one thing
this
is,
is very similar to what I also done in the past. So do you have a link to your open source library?
actually, I started yesterday, but you can follow me on GitHub. I mean, it's my name, surname, so.
Yeah, I will.
Uh,
Did they
Ardo Musnet.
just change GitHub?
What?
They just change it.
Mm-hmm. This change it, yeah.
What the
So tell
fuck?
me this thing, Ricardo, how did you install Xformer? Xformer is not getting installed in my system.
Oh, so 2020. So they recently had the wheels, so they are pre-built. Which system do
Okay,
you have? Which
M2.
CUDA version? Oh man, so you can't use it.
Fuck.
Yeah, man, you
Docker,
need to
Docker.
stop. No, it's a matter of the hardware. So Xformer will give you some highly optimized kernel for CUDA to make things running faster if you have NVIDIA GPU. Uh,
Okay. I think I have to look for cloud solutions, Lambda GPU type thing.
yeah, but yeah, for automatic 1111.
Yeah.
Yeah,
The story is
uh,
same.
yeah. I mean, I don't know, like
Oh,
I was able to install all the optimization on my Ubuntu machine for automatic 1111. Like I'm able to generate an image in 3 seconds. I don't know if you're able, if that is like way faster compared to the M2. I'm kind of curious about that because I also have an M2 machine and an M1 as well, but I haven't tried them because I just have also a GPU. I was kind of curious. I don't know. Like, how much does it take for you with the M2 to generate an image?
It takes time. It takes quite a time because
Okay.
I don't have a GPU. I have Apple M2 Silicon chip, and Silicon chip is different from this NVIDIA.
Yeah.
Consider it as CPU only. So
Yeah.
it takes, I think, 7 seconds, 8 seconds, sometimes 10.
Okay. Okay. Ah, yeah. So this is the good Lucid Rains X
but let
transformers.
me let me see. Is from Meta? Is that? Mm,
No. So this is the original implementation, but
no, this is
but
not from Meta. Wait. Uh,
implementation.
GitHub Meta iJEPA.
I cannot find it. Are you
Oh,
sure?
I found it.
Oh,
I
nice.
found it. Where I have to share here
6 days.
some link. Is there any
Here
part?
on the Discord on the papers.
Share your screen. That's it. It will be shared.
Okay. Okay. Sweet. So nice. All the models here. Sweet. Uh, okay. So let's actually have a quick look inside. So I can see a config here, which is not usually a good sign. Is
Um,
this on the Tetrum 2 sheet? No.
I just see your Google page.
Lol.
I don't see.
Yeah. Sorry.
Yeah, no, yeah.
Okay. What
Yeah,
is
but the config is quite, let's say, easy to understand to me. I mean, it's not.
No, but I mean that usually is not a good sign because that is usually uh, what is going on with with GitHub? Why I cannot understand shit anymore? Why there is too much stuff here? What's going on? I
Yeah,
just
yeah. But to me, it makes sense because I mean, now you can look for functions and methods and classes. I
yeah,
mean,
but I was not used to that. Like I mean,
yeah, yeah, yeah. I
like
know, I
in
know, I
my
know.
way of thinking, like you should tell me that, hey, this is the new one, you know, and then
You
I
wanna
need to
try
have
it?
a
Yeah,
toggle to say I want to have the
yeah, yeah.
old one so I can get used to the new one. Okay, so here we have all the vision transformer thing, all the good stuff. Okay, okay, and so this is bad. This is very bad. It's kind of funny that Facebook doesn't know that in PyTorch they have a very good way of compute attention, and this is low compared to the PyTorch one. Or because with the PyTorch and multi-head attention, you get with PyTorch 2 like the fast X-former attention by default. By doing this, you don't have quasi-linear attention. So I don't really understand because I guess that they could have decreased the train time by some good amount by just using the PyTorch already implemented attention.
To me, they don't give a shit. This is just
Yeah, they
open
don't give a
source
shit.
code. Yeah, they optimize the code afterwards. This is my opinion because, I mean, I don't understand how engineers from Meta, we're talking one of the biggest companies in the world that does AI, write like code like this, which
No,
is a mess.
so
This
that's
is just a
because
face value code.
yeah,
Yeah.
no, I mean like his code is already way better than usually research code, you know. Like there's some comments around the code is what is this shit? The code is easy to more or less follow. So cheaper things convolutional time for VAT follow VATC models. Fuck. Uh, so what
But
is
this
so
generated with AI
no
seems like code
so
is generated.
so this is so this is a different stamp that I don't know when they use it. So that is what is VATC? I don't know.
Yeah. Yeah.
I mean,
Look for the.
I think it's like it stands for VAT convolution, right? There is a convolution here, and my god, this thing is so annoying. This thing is so annoying. Okay, then we have the predictor, right? Then it's this one. Then what is going on inside? So I take away everything that I was doing before. I was saying before. Vision transformer predictor. Here we have so man, this thing is so annoying because it basically they decrease the
Yeah,
space here.
every time you click, yeah.
Yeah, it's so stupid. Like I'm reading the code. I'm doing this. You know, like I'm doing this, and then it's oh yeah. Every time I click, okay, I got that. Okay, so I guess this is the okay. This is the predictor position embedding. Yeah. So okay, so this is the mask token. For fuck's sake, this is the mask token, right? And then
Yeah, the mask token, if you see,
I
you
kind of
have.
wonder like why do you do this to initialize the mask token? Is this some common knowledge that I don't know? Drop normal. So why do
I
you?
see. Yeah, I see this initialization like in
Everywhere.
most of the implementations, but actually, I don't know why we did that.
Then it's a given, right?
Sorry?
Then it's a given.
Yeah, it's a given. Yeah.
Okay, here we have the mask token. Okay, so the mask.
So if you see the mask token dimension is that one by the predictor embedding. So as we were saying, so the mask token is related to the mask, which has the same size of, let's say, of the embeddings of each patch. So if you have, I don't know how to say it, like
Like I
100
mean,
patches.
it has the same size of the number of tokens, right?
Yeah,
Those,
right.
okay,
Yeah,
okay,
you're right.
okay.
Yeah,
So
you're right.
yes, so that will be like like it's the best size, the what people call the sequence length, and then the embedding, like the embedding
It should be like this,
the
but I
sequence
mean,
length.
it's just my opinion. I mean, I don't know if it's true or not. Again, I try to let's
Okay,
say experiment with
so
this
wait,
kind of
here
stuff
we have.
to understand. Yeah, just to understand how it works.
So this is kind of interesting. Okay, we are predicting embed, so here we get some X. So math from encoder dim to predictor. I should make a PR just changing this. Predictor dim, positional embedding to X tokens. Okay, apply mask, and then in apply mask. Okay, so this time this is useful. I go here.
Then you have the definition somewhere, maybe.
No, it's
Wow, but it should
wow.
be
It's
the definition.
so useful, so useful.
But I saw some other
Yeah.
other GitHub repos with that they bring you to the right
Yeah.
file
But
by
by the
clicking to a
way,
function.
also, yeah, I see this. I saw the same one. By the way, how cool and polished is GitHub new design? I really like it so much. It's so polished. Okay. Apply mask. We get X and mask. Ah, okay. So here, sorry. Apply mask. Oh my god. Okay, so here we are applying the mask to the position embedding. Yes, of course. And then concat mask token to X. Man, I don't really know what is going on here inside, but I think it's getting a little too late for me. So I think here, like I mean, you need to mask the positional embedding, right? And then we are incorporating into the embedding the mask positional embedding, and we are concatenate mask tokens to X, of course, because we have the mask token, so we need to concatenate and concat mask token to X. So here I don't really see the concatenation here. Here we are repeating the position embedding. We are masking the position embedding. So here we have, okay. So we are predicting two positional. Wait, this is, why are we doing this two times? So this is X position embedding, is this thing, right? Which is the same thing as this one. Yeah, because in the first here we use the mask for X. Here we use the mask, I guess, for the target.
For the target, yeah.
Okay, and then I think we got this position embedding. We are adding the position embedding to the mask token. Yeah, because the mask token is used. Yeah, of course. We add to the mask token the mask for the targets, and the mask token will tell us basically, hey, the target are not there and are in the other position, I don't know. Then we concatenate. So it means that here we have the mask information from the X. Here we have the mask embedding, sorry, mask token, right, that carries the information about where things are in the targets, and then we do the prediction, and then we remove the mask token. So here we are doing the prediction, we are doing the normalization, we remove the mask. We are sorry. Yeah. We just take the mask token, of course, and then we do that. Okay, it makes sense, right? Actually, right?
Yeah.
Yeah, because this is in the paper the X I, and the MJ where J was in BI, right?
MJ was in, yeah.
Yeah, because this is just the mask token with the mask of the target apply on top, basically, like on that one. And it makes sense.
In
So
any case, I will do some kind of reverse engineering and trying with stuff just to understand this kind of stuff.
yeah, so like usually the best way to do that, in my experience, is just try to import the model that you want, like try to understand the input that you need to
Yeah.
pass, and then you put a breakpoint, right?
Yeah. What I do is, as I was saying, is taking this kind of repositories here, and let's say try to build like a fancy way. I mean, like a proper repositories that you can install and blah blah blah.
Yeah, I was actually doing
Yeah,
the same thing, right? I don't know if you know it. Then it was more about normal model. So I was doing this. Uh, 31, damn. Okay. So basically, this is a repo with a lot of models. So you can just import them and use, right? And but then these were made mostly for normal models. So then I was starting to work on a V2 that then I don't have time to work on that anymore. But basically, the goal was basically to do something similar, but in general for any computer vision model, something similar to transformers, but that you can actually, do whatever you want, because transformers, the repo for Mac interface, is not a toolbox. It means that you can change anything inside it because it's not made to be a toolbox. And then each model is implemented in a single file, so you have file with 3K or 4K lines there. And when I was working there, it was a nightmare to work with, because like you just need to scroll a 4K 5K lines file. So that, yeah. Oh, I was why to do something like that, because the Tectron 2, sorry, is not so great. The ML lab stuff, it's slightly better, but still. So like I want to do something similar to Transformer, but with the toolbox of the Tectron 2, but that you can train with Lightning, so you don't need to reinvent the wheel anymore. But then I'm kind of busy to other stuff. But
Yeah.
it would be cool
I do
to,
that in my spare time. Yeah, of course.
yeah, like
Also.
it would be cool at some point to maybe, yeah. I have to continue on that, and I guess it would be cool to find if there are some other people around that are trying to do something similar and try maybe to merge ideas together, because I think that in the computer physical community that is super missing. I will just like in my ideal world, I will have to have some sort of library that I can install. I take the model that I want. I need to follow maybe a little bit of interface, and then I just call a train method, and the train method is actually called is actually a lighting module. So if I need to pass if I need to pass a callback or something that I don't need to learn a new stuff. I can just read the lighting documentation, which is very good.
I did the same. I did the same for the task of saliency detection.
Nice.
I created a library called Saldet,
So,
which is
do you want
Saldet. Yeah.
to share it here?
Yeah, I mean you can open. I mean if you look for Saldet,
Saldet?
yeah.
Maybe.
But yeah, that one.
Oh, here we go.
Yeah, and if you go, yeah, you can install it
Also give
with,
you
I mean,
the
pip install.
follow. So let me also give you. How can I? Okay, here.
Yeah, if you go on the README, so if you, I mean, look at the README, so you have some models because, I mean, of course, you don't have a lot of saliency detection models. But I tried to, let's say, put together, yeah, all the models, and also, as you were saying, you have some kind of interfaces with PyTorch
Yeah,
lighting
this is
that
great.
allows you to do training inference, and also if you want to do, let's say, what is if you want to do something more, let's say raw, you have the PyTorch experience, of course, because you have to what you can do is just doing create model like the team library, and so you have all the options. And so, but I feel you. I mean, this is what I mean, my company is what we do actually. So we try to get the best out of repositories and wrap around some kind of, easy way to train and inference. So yeah, that's
Yeah,
Quite cool.
it's great, man. Yeah, I really like the fact that
Maybe Ricardo, you can get help in while transferring these files into Docker or something, and maybe you won't face that much issue while running.
Oh no, I think that he was talking more about the fact that people have issues when they try to run the open source projects because
yeah,
they
yeah,
they don't even have a requirements file
yeah. It's a
most of the
mess.
time.
It's a mess. And if you have to, I mean,
Yeah.
I think that is
So let's
very
see.
interesting. I mean, yeah, using this
Yeah,
kind
yeah.
of stuff.
Here,
Yeah.
Unethical. Quite
nothing
unethical it
to
is
install,
without
man. Here,
requirement.
look. They have a
Yeah,
fucking code of conduct. Okay. They don't have
So,
a
so
requirements
Ricardo
file.
just said that this is just a face value code, means the real code must be existing in somebody's system.
Yeah.
Yeah, I mean, I guess,
Working.
guys, I don't think Facebook
And
doesn't
one
have like.
thing is that these some repos. So if you look at where the hell segment anything repo. So that was very special because this was a real official release that you can feel the quality of the code here. So
Yeah.
here you have a lot more stuff. So that was kind of interesting, and I would like to know why this model that is super cool, right? But why it was specifically choose to be released in this super polished way, because like they made the blog post, they made the demo, they made all the videos. Here it's very well 35k. Fuck. Here it's it's always, yeah, it's very well done.
Yeah, but then
And
if
you
you go
have
to
a
the
step
Dino
here, right?
repository,
That you can.
yeah, if you
What
go
is
to the
this stuff?
Dino repository, it's a mess. Have you ever seen the Dino repository? It's a mess.
Yeah.
Dino is shit. In Dino, you cannot install properly.
Dino is shit. I mean, you have scripts all around the repository, and
What the fuck
I
is
can.
this stuff? Main underscore Dino. I'm so sorry to shit upon
Yeah.
the yeah, but like what? So like to me it's crazy. So you're into Facebook. Like if you are a very good scientist, but you don't know how to code, can you just reach to an engineer team and say, hey, we are doing this. Could you please advise us how to package it? In order that then so people can actually install it.
Yeah, because you release open source stuff, but then it's a mess. I mean, and it's not. I mean, even though it's open source, but people have to spend a lot of time, to refactor the code so that it's easier to
Yeah,
use.
but like to me, there is actually a difference between open source something and like truly be open. Because if you're truly open, it means that like you're also opening like the knowledge. So you means that you make accessible the knowledge of using this code. So you're not just making accessible the code, but also making easier to me to get starting, and that's truly be open in that way, I guess.
But also Microsoft does the same thing, I guess. If you go to
Everybody.
SVit, repository, I mean, but at least I can understand Microsoft since they have
SVT?
all the services as VIT, VIT.
Sorry.
Yeah,
What's SVT? Svite. What was Svite? I remember.
but it's like training. If I remember correctly.
So they
advice
change
where
all GitHub, but their service is still shit. I don't understand that. I complain a lot tonight about. I don't think it's this one, right?
I don't. I see still segment anything. I don't see the other stuff. No. Look for efficient self-supervised vision transformer, and then you get the repository.
Okay.
Yeah,
ASVT. Yeah.
yeah,
I store it already.
Microsoft.
I store it already. So what was the catch with this one?
I don't remember, but they trained like VIT with self-supervised method. I don't remember what was their claim here. But see, the repository, it's like it's not as a mess as the ones from Meta, but still, to me, it's not.
So let's see actually on papers with code the.
Yeah, Dino V2. And if it's let's see the code from the
Yeah,
Dino
yeah.
V2. It's a mess. I
Let's
mean,
do
I'm
that.
quite sure it's a mess.
Okay, we have requirements here.
Okay.
Good.
We don't see
Asset
anything
up.
here.
Okay, sorry. We have a requirement. Okay, apologies. I hit the wrong button here. So we have our requirements.
Okay.
Our
Oh,
requirements dash dev. Ah.
okay, at least at home. Oh, wow.
Ah.
Maybe they improved.
Oh well.
Wow. Everything on
So let's
kind of
look at
stuff.
the train code. What's going on here? We have some stuff.
Oh my God, I had this kind of code.
I really like how, perform teacher em update. Can you just call this model dot update teacher with ema? Yeah, mom.
Mom.
Come on. Okay, I mean it's
At least they made some progress.
yeah. Mr. Robot, we read this paper together. Yeah, remember that we were trying to get the video that we cannot get it anymore. Yeah, I remember that one.
What's the difference from the version 1? What is the difference?
You're asking too much now. I don't
Okay.
remember. I
Okay,
don't
okay.
remember.
Only there is evolutionary change between Dino and Dino V2. The way they have changed so that they can capture something more. That's it. There is
Okay.
not any structural change in model.
Okay.
Just like fine-tuning steps
Okay.
and handling and like the initial steps, so they handle data.
Okay.
Yeah, so
They have mentioned in the first para only. Yeah.
yeah. Like they changed the way that they source the data to have more quality data.
I think this is just for PR purpose, so that Meta also lives on the internet.
Yeah, and
Nobody
another
forget
thing
that.
is that they train
They
on
will-
1 billion VVT and then they distill it. Damn.
Okay. I mean,
They have,
more to do
you
that.
can see that they have written VIT and Dostoevsky. Usually nobody writes this. They have written because they have nothing to display here. It's just a formality paper, Dino V2. Dino 1 is something, means they have explained well. Because when I was reading Dino V2, then I realized that first I have to read Dino V1. And Dino V1 will explain, like,
Yeah, but
this is just
it's
extension.
quite funny because his whole paper could basically be a blog post, because like I remember, I mean it was very good, but it was so cumbersome to read because there was too much information that
Dino
was
paper
not
is
really so.
Dino paper is good, no doubt. Means the way they have means
what is
using.
wait a second. So what is this? Patch.
You want to see this? There is one more paper called "See Everything at Once."
Yeah. But no. But see, so that paper is specifically for the task of doing that. But this is basically a little hack. So they have the image divided into patches, like on the left, on the right, and then they match the similarity with each other patch. So this is a good thing. I never thought about it, but this is actually a useful hack that you can use, right?
You can check this paper.
Yeah.
Yeah, this is something which has potential for you will see this only in highly magnified way in this paper, which see everything at once. I think this will be useful in warfares and weaponaries, not in something good.
Yeah, maybe we can read that for the next time.
Mhm.
What do you think? Well, yeah, I mean, I think that's all, right? I mean, we did a very, man, it's almost 2 hours. Uh, we did a very good session. It was very interesting. Very interesting. And yeah, I learned a new
Something
thing
is
today.
compared in non-living to living thing, I think. The semantics between the living thing and non-living, like the picture of